This will be the first video in our waves and sound unit, and we will talk about the basics of waves, some basic vocabulary that you need to know. First of all, a wave is an energy transport mechanism. Waves move energy from one place to another. So when a wave is traveling, it is energy that is moving. Get my pen open. There we go. Energy is traveling. What is not traveling? Material. It's called the medium. The stuff that a wave is traveling through is called the medium. And the medium isn't moving from place to place. It is energy that is moving from place to place. Waves are disturbances that move away from some source. And let's think about examples of wave that show that energy and not the medium travels. So the first thing, if we're at the ocean and ocean waves travel by, we can see a bird sitting on the wave, and that bird will move up and that bird will move down. But that bird, while the waves are traveling this way, is not going to move along with the wave. Now I know that when you get close to the shore and waves break, they're a little bit different. But when you're further out and you get real wave motion, the bird does not move in. Let's see, another one. Okay, I like this example. Have you ever been to a game, a football game or a soccer game, and done the stadium wave? So you have all of these people, and these people are sitting in their seats, and when the wave comes by, each person stands up and sits back down. So you get something that looks like, this person is standing up, and this person's sort of half up, and this person's half up, and then this person's sitting down, and then the next person is sort of half up, and this person's up. So you get this wave motion, but the people aren't traveling. They are moving out of their rest position, but they are not traveling along with the wave. But if you were looking from a distance, you could see that wave impulse, that energy travel around the stadium. There are two kinds of waves. There are electromagnetic waves and mechanical waves. We aren't really attached to chapters, but if you have a textbook or if you would like to look something up, electromagnetic waves, well, that's light. And we'll talk about that. That's our next unit. And that's chapter 16, 17, and 18. But right now, we're going to talk about mechanical waves. Mechanical waves are waves that actually move through some material medium. Mechanical waves must have stuff, a material medium to travel through. Electromagnetic waves, like light, do not need a material medium to travel through it. And you can tell that just by sunlight. Sunlight gets here, their space is an empty void, and yet the light can travel through that space. Sound would not be able to travel through that space because sound is a mechanical wave and needs a medium to travel through. So later we'll talk about electromagnetic waves, but right now we're going to talk about mechanical waves. And the subtypes of mechanical waves are transverse waves and longitudinal waves. A transverse wave is a wave in which the particle displacement, the particle would be particles of the medium, so the water when a wave passes through water, or the ground if we're talking about an earthquake wave, or the people if we're talking about a stadium wave. So a transverse wave is a wave in which the particle displacement is perpendicular to the wave movement. So I'm going to talk about a water wave again. If you're at the ocean, you see these swells, you see waves that look like this. And if I have the bird sitting on top, that bird will move up, and that bird, if that bird's friend is over here, that bird will move down. A flat ocean would look like this. So birds bob up and down and up and down, moving perpendicularly to the direction of the wave travel. The wave would move in this direction. So if the displacement of the medium, the displacement of the particles that are moving because of the wave, is perpendicular to the direction of wave travel, then we have a transverse wave. And this has been an example. A stadium wave would be, I can't spell it, stadium wave would be an example of a transverse wave. A water wave is an example of a transverse wave. Earthquakes actually have both types of waves. When you have an earthquake, the ground you get a rolling feeling, and that's because of the transverse component of the earthquake wave. But the earthquakes also have longitudinal waves. Let's talk about longitudinal waves. Okay, this is pre-drawn because I don't draw longitudinal waves very well. A longitudinal wave is a wave, and these are the same words as before, a wave in which the particle displacement, so what you wrote down before, is parallel to the direction of the wave motion. So if I had a slinky and it just looked like this when it was sitting there, and I pinched it and let it go, what I would see is that that pinched part would travel, and then we'd have a stretched out part, and then a pinched part, and then a stretched out part, and then a pinched part. And this is a longitudinal wave, and what happens is the particles are moving this way while the wave moves along. So if you tied a ribbon around, it's supposed to be a bow, if you tied a bow around the slinky, that bow would move back and forth along the direction of wave motion, along with it and then backward, back and forth, parallel to the direction of wave motion. So this bow would move this way and then this way, and the wave is moving this way, and those are parallel. So a longitudinal wave is a wave in which the particle displacement is parallel to the wave motion. I'm going to back up just a minute. In a transverse wave, and this is said later in this video, or we'll say it again, transverse waves have high points that we call crests, and they have low points called troughs. A longitudinal wave has an area of compression, like here, and these areas of compression are called compressions. They are positions of high pressure, where the particles are smushed together. And then the areas of low pressure, like here, and here, and here, and here, are called rarefactions. That's R-A-R-E-F-A-C-T-I-O-N, rarefaction. So we have compressions where things are smushed together, and rarefactions where things are spread out. Now what is this weird picture over here? It looks like a sideways eyeball. This is supposed to be a sound wave. Sound is a longitudinal wave. And this is supposed to represent a drum head. So the drum head sits there, and then somebody hits it, and the drum head vibrates back and forth. So the drum head would move out, and it would smush the air in front of it and make it all tight and compacted. And that compacted area would move along, and then the drum head would move back this way and be over here, and it would cause an area of low pressure, or rarefaction, to also move along. So that's how sound waves are made. Something vibrates, and you have areas of compression and rarefaction that move away from the source. So sound is our best example of a longitudinal wave. If you were in class, I would pull out a slinky, one of you would hold one end and I'd hold the other, and I would show you. I would move the end of the slinky up and down and create something that looks like this, and then I would move the slinky back and forth and create something that looks like this. The compressions are kind of like crests, and the rarefactions are kind of like troughs. Okay. Some other vocabulary we need to know. Amplitude. Amplitude is the height of a wave measured from the equilibrium position. So if I have a string, and then I send a wave along that string, the amplitude is this height, the height above the rest or equilibrium position. It can also be measured from the equilibrium position down. So those two things would be amplitude. It is not the top to bottom. I hate to draw something that's wrong, but it is not from here all the way down to here. That is actually called wave height, and that's not really a physicsy word. So I'm going to undo and take that off. That is not amplitude. It is from the wave down to the equilibrium position. Frequency is how many oscillations happen every second, or cycles per second. The symbol for frequency is a lowercase f. The unit for frequency, even though it is cycles per second, there's a name for it, and it's called a hertz. A hertz is a cycle per second. How many waves, oscillations happen per second, and the symbol for the hertz is Hz. The wavelength is how long a wave is. It's from one point to an identical point on the next wave. So let's look at this wave up here. So here is a crest, here is another crest. The distance between those is a wavelength, and the symbol for wavelength is the Greek letter lambda. It's drawn like that. It's not a great lambda, but anyway, something like that. And it is measured in meters. It is a length. You can also measure it from trough to trough, or from any point on the wave, like right here, to the same point on the next wave, like right there. That would also be a wavelength. The period is the amount of time required for one cycle to happen. So period is actually the inverse of frequency. Frequency is cycles per second. Period is seconds per cycle. The period is a time, and it's measured in seconds, and the symbol is capital T. It's a very special time, so we give it the capital T. Frequency is 1 over the period, and period is 1 over the frequency. For example, if I had a frequency of 4 hertz, then the period for that wave would be 1/4 of a second. If 4 cycles happen in 1 second, then it would take 1/4 of a second for each of the cycles to happen. So this is most of the basic wave vocabulary. Okay, and labeling parts of a wave. Again, we've already talked about the crests, and we've talked about troughs. These are the bottom points. I'm going to see if I can erase everything on. There we go. So the crests are the tippy top places, and the troughs are the very bottom places. The equilibrium position would be like if the string did not have a wave traveling across it, so it's this place kind of in the middle. And amplitude is from that equilibrium line or the rest position up to or down to the maximum displacement. So an amplitude can be measured up or down. So, and wavelength is the crest to crest distance. Okay. One last thing, we need to talk about wave speed. This is called the wave equation, and the speed of a wave is equal to that wave's frequency times that wave's wavelength. Remember, frequency is cycles per second, so it's a 1 over second, and wavelength is a meter, and if I multiply those together, I get meters per second. You can still calculate velocity as change in position over time, or distance over time, but this is just another way to calculate the velocity if you have a wave. So given any two of these quantities, you should be able to calculate the third. And that is the end of wave basics. So no, it's not quite the end. It's almost the end of wave basics. I need to tell you one more thing. The wave speed depends on the medium. And what do I mean by that? The speed of sound is about 343 meters per second at 20 degrees Celsius in air. So if I have a flute player playing a really high frequency sound and a tuba player playing a really low frequency sound, those sounds travel at the same speed. And you know that because you've been to concerts. And if you see a tuba and a flute play at the same time, you hear the two sounds at the same time. So wave speed does not depend on the frequency of the wave. It only depends on the medium through which the wave is traveling. If I turn the temperature up in the room, I said it's 343 meters per second at 20 degrees Celsius. If I turn the heater on, the speed of sound would be higher. It travels faster in hotter air. If I chilled the room down, the speed of sound would be lower. But that's a characteristic of the medium, the temperature of the air that the sound is traveling through. So wave speed depends only on the medium through which the wave is traveling. And that is the end of wave basics.